Okay, we left off, we were talking about properties. Now, we talked about all this stuff, right? We made it all the way through distributive, okay? Is that correct? Okay, I think we were just leaving off, you were able to name the properties that were illustrated, and we kind of left off down here, I think, on additive and multiplicative inverses, right? Remind me real quick, what do we mean by an additive inverse? What is that? What's the additive inverse of A?
Negative.
Negative A, good. Additive inverse is just the opposite, right? Because the job of the additive inverse is what we add to a number to get back 0, which is the identity number for addition, right? Now, what's the multiplicative inverse? Right? Reciprocal, sure. So the multiplicative inverse, which means reciprocal of A, would just be 1 over A. And the job of the multiplicative inverse is it's what I multiply a number by to get back my identity number for multiplication, which is 1, right? So, for example, for the square root of 10, what's the additive inverse?
Negative.
What's the multiplicative inverse? Now, you're probably thinking, I can't have a radical on the bottom. I don't care. 1 over square root of 10, right? You could rationalize that denominator if you want to. That's fine. But that's same thing, right? Good. Okay, last issue then. Last issue is the closure property. And we didn't get to this, right? This is kind of where we left off. Okay, so the closure property, this is interesting. The closure property just says this: a set is closed under a given operation if every time you apply that operation to any elements in that set, you get back an answer that stays in that set, okay? So for example, true or false, the set of integers is closed under multiplication. That is true if every case of multiplying 2 integers gives you an answer that is also an integer, okay? If you can find even one counterexample where you multiply 2 integers and you get a result that is a non-integer, then that set is not closed under multiplication, okay? So think about this one a little bit. Is the set of integer closed under multiplication? Now, you can't consider all infinite possibilities, but you could probably make some blanket statements about integers. If I multiply 2 integers together, is there any way you could get an answer that's not an integer?
Yeah.
No, there's not. Do you have an idea? No. Okay, so yeah, you can't. Multiply 2 integers, you're always getting an integer. And so that's a true statement. That's a set that is closed under multiplication. Okay, what about irrational numbers and subtraction? Is the set of irrational numbers closed under subtraction? Like, for example, if I subtract the square root of 2 from the square root of 3, I get some weird irrational number, right? So that seems to work. You can find lots of cases where it is true, but can you find a case where it's not true? Can you find at least one case where we can subtract 2 irrational numbers and get a result, get an answer that is not irrational, not an irrational number, sorry. Pi minus pi, why not? So what if we did something like, so this is false, and an example, a counterexample would be pi minus pi equals 0. Is 0 irrational? Can't be. Justify. Why is 0 not? What is 0? It's a whole number, isn't it? Yeah. Good. So it's got to be rational. Okay, is the set of whole numbers closed under division? What's a counterexample of that? 2 divided by 3. There's one. Sure. So if we take the whole numbers 2 and divide that by 3, I get 2/3, right? So that's false. 2/3 is, that quotient is not a whole number. Good. The set of odd numbers, is that closed under addition? Mm-mm. And I don't think there is a single example where it actually, an odd number plus an odd number, I think it's always even, isn't it?
Yeah.
Right?
Always.
So that one's clearly false. Like 1 plus 3 equals 4 would be my counterexample, right? Okay? So you get the idea. Now, on the assignment, I'm going to introduce you to the assignment here in just a second. You'll get a chance to go through these. For you guys, this will go really quickly, I'm sure. But I want you just to get, today is as much about getting familiar with Moodle as anything else. You'll get a chance to look at some pretty basic, some of them are a little harder than this, but some pretty basic examples. But once again, I just want you to realize that if you were to peer ahead mathematically down the road, this idea of closure is a really big deal later on in math. If you look at sort of some theoretical math classes, if you were going to be a straight math major and you were going to look at some ring theory classes and some theory of math classes, that's an issue that comes up a lot. Is a certain set closed under an operation? And you can even do things like really bizarre, like you could look at topological math. If you look at topological math, topologically, what do you think? You tell me. Just fun little brain teaser here. Let's take two different kinds of, like a frisbee, a traditional frisbee, which is just a disc. And then what are those things with the holes in them? Are they aerobies or something like that? You know what I'm talking about, where it's like a frisbee with the center cut out and they go really far. You know what I'm talking about?
Yeah.
Okay, let's take three elements here. We've got a frisbee and an aerobie, and just, I don't think I've got one with me, but just like a regular coffee mug, where you can grab the handle and take a coffee mug. Which of those two things seem the most similar topologically? The frisbee and the what? The frisbee and the aerobie probably, right? No, it's not. It's actually the aerobie and the coffee cup. Anybody know why? Because they have a hole. Yeah, because they have a hole in them, right? They both have a hole, and it's easier using topological math. It's much easier to transition from like a hula hoop or an aerobie to a coffee cup by just redistributing all the matter in the, to kind of like think of it being clay or something, right? You could kind of mold the clay, but you retain that ring. Each of them has one ring. And some of the rules of topological math, it's really hard to break rings. Breaking rings is a big deal, but you can redistribute the stuff in a ring pretty easily, right? And so there's some weird kinds of math where you might ask questions like, are certain topological entities, are they closed under folding? Things like that. There's some other weird kinds of operations that look much different than this, but it's the same concept, right? It's the same mathematical concept of closure, of set closure, okay? Well, as the year goes on, we'll talk more about that weird stuff, but just want to kind of get you thinking ahead a little bit. Okay, so everybody grab Chromebook real quick and get logged in. I want to start looking at the next handout. I think I already gave you. We might look at a couple sample questions, but I want to just get you thinking about the difference between these three verbs in math. What do they mean? When they ask you, a lot of times we'll ask you to solve equations or solve inequalities or something like that. To solve something, we'll ask you to simplify or we'll ask you to evaluate. And I think a lot of times math students sort of don't really know what the difference is between all of those things. So if we're solving an equation, let's take a really simple equation. What do I do to solve that? Solve for x. What do I do? I add 3 to both sides, of course. I get 2x equals 12, and then I divide by 2. So really all I did is I worked to isolate the x, right? Okay, if I solve an equation like that, what I'm trying to do is I'm trying to find all of the values of the variable. In this case, there's only one variable. All the values of the variable that satisfy the original equation, right? When we say the values that satisfy the original equation, we mean that make it a true statement, right? So that's what solving is. Solving, we're going to get values for the variables, right? We're going to come out with number values probably, okay? What about simplify and evaluate? Simplify and evaluate, I think, are easier things to do. Solving usually is the hardest thing we do in algebra. These are typically a lot easier, right? Okay, so if we want to, for example, we want to simplify an expression just involving numbers, a numerical expression. Okay, let's take a look at a couple of these. Let's look at, how about that one first? How are you going to go about doing that? If my job is to simplify this, what is the end result going to look like? If I've just got a bunch of numbers in an expression up there, and I want to simplify that, what should my end result probably be? Probably just a number, right? We want to turn this, this mix of different numbers and operations into its easiest, simplest form, which is going to be a single number, okay? How do we know what to do first? Yeah, this is just order of operations stuff, isn't it? Okay? So when you write order of operations down, one thing you probably already know this, but this is a really big deal. Y'all PEMDAS, right? You know PEMDAS or GEMDAS, or how'd you learn it? PEMDAS. Yeah, that's fine. I learned PEMDAS. So if we do PEMDAS, here's how you have to write it though. You want you to write it vertically like a tree. The P goes to the top, and then E, and then do I go M and D separately? No, I don't. Those are equal, right? Multiplication and division are on absolutely equal footing. Neither one goes before the other one. And then the same thing with addition and subtraction, okay? Order of operations tells you a ton of stuff in algebra. You get a lot of mileage out of this. If you use the regular, what you're used to, the regular top-down direction, that's the direction that we travel in the order of operations tree when we are simplifying. Is there another way to use that tree? Would there ever be a reason to reverse the direction? What are you doing when you reverse the direction?
When you're checking your work. When you have a very long segment.
When you're solving, that's it. When you're solving an equation, if you're solving by isolating the variable, like we did in that last example, all you do is reverse the order of operations, and that tells you the order in which to do things. Now, most of the time, you're obviously very good math students. This is so intuitive to you that you don't even think about it in terms of an order of operations, but you are following it without even knowing it maybe. But there are times in the future when we get into more complex stuff where we can extend this, and it might be useful to know that this is actually what you're doing, right? Okay, so let's go back to this one then. What do we got to do first? Okay, the P for parentheses, what does that really mean? Not just parentheses. Any kind of a grouping symbol, right? Anytime in an expression where things are grouped somehow, they're implicitly grouped, or they're grouped inside symbols, then that has to come first. So step number one, has to be, we're going to deal with that grouping symbol. So what is the absolute value of -8? 8. So that makes it a 4 cubed minus 8 times 6 divided by 16. Okay, step one is taken care of. We can move down. Done with grouping symbols. What's next? Exponents. Okay, so exponents, where do we see an exponent? Well, right there, right? What's 4 cubed?
Right there.
64. There you go. So we get 64 minus 8 times 6 divided by 16. So we're done with that one. Pick it up tomorrow. There we go.